So hello everyone. In the last video, we have talked about the different range of topic, including the Boolean algebra and the combinational circuit, especially marks. Then we have talked about the flip-flops and the counter, and we have seen the previous year question based on these topics. So today, since in the previous year question we haven't seen any question from the number system, so today I'll be like there is a high chance that this topic uh, may come in the upcoming examination, and this is a very easy topic. So let us just go in the important points and important conversion techniques in the number system. But before that, if you are watching it for the first time or you are new to my channel, subscribe it and then go to the playlist named as DCIO Tech 2025 and check out the different important videos in it on various topics that may be beneficial for your preparation for this exam. Also, I will be uploading the notes of today's lecture as well as the previous lectures. Notes are already available on the Telegram channel, which you can search and find it on the URL t.me AP, that is Aayu Pathshala DCIO 2025 or 25. Just search for it and you will be able to find the Telegram channel. Do join it and you can download the notes available in the channel. So starting with the number system, let us first begin with the like the most general number system that we are used to, and we use it in our daily like day to day mathematical calculation. That is the decimal number system, and we will start building our concept from this general number system. In decimal number system, we are aware that we have different numbers, different unique numbers starting from 0 up to 9. That is total 10 different numbers in the decimal numbers. So others number, that is like any counting we do in the decimal, say 21, 23, 28, or say 1024. All these numbers are nothing but the combinations of only these 10 unique numbers. So in a decimal number, these 10 unique numbers basically forms the base of it, and therefore we say that the base is 10. When we say the base is 10, it means that there are 10 different numbers in it, and that ranges from 0 to 9. Similarly, if we say that the base of any number system is 6, suppose we say that the base of any number system is 6, it means there are 6 different numbers in it, and it will range from where? 0 to 5. Similarly, if we say that if there is a number system with base A, and why basically we talk about the number system is because we may expect questions on it, because the last 2 years there is no question on number system. So this year might be one question from this topic may come. So base 8 means we have 8 different numbers, and it will range from 0 to 7. Similarly, if we talk about base 16, then we will say that there are 16 different numbers. So what could be the different numbers? 0 to 9, that is 10 already. So 0 to 9, we have 10 numbers. Then what we may have? We may have A, B, C, D, E, and F. So these 10 numbers and this 6 alphabet. If we are like falling short of the numbers, we may use alphabets. So 0 to 9 makes it 10 different numbers. Then we use 6 alphabet, that is from A, B, C, D, E, F. This 6 and this 10 makes total different unique identifier as 16. So suppose if we have base 12, so what would be the different unique identifiers in it? Like we have to include 0 to 9, that makes it 10 different numbers, plus we must have A and B. So the different numbers in the base 12 will be from 0 to B, where A is going to represent what? A is going to represent 10, B is going to represent 11. Okay. Similarly here, A is going to represent what? 10. Up to 9 we have here 9. A is going to represent 10, B is going to represent 11, C 12, D 13, E 14, F 15. That is what we have in base 16 up to 15. In base 10 we have number up to 9. In base 6 we have number up to 5. So therefore in base 16 we will have number up to, maximum number will be up to 15, and 15 will be represented as F. Similarly in base 12 we will have maximum number up to 11, and 11, that too will be represented by V. So if this is clear that how many different numerals we are going to have, or different unique identifier we are going to have in any base number. So if we say that base is 2, we may have only two unique identifier, that is 0 and 1. If we say the base is 2, we have only two unique identifier, that is 0 and 1. So, friends, this base 2 number system is known as binary number system. This base 10 is called as the decimal, that we have already seen. Base 8 is known as the octal. And base 16 is represented as like hexadecimal. Hexadecimal. So now, suppose if I say that binary number system, how many different unique combinations we have? Only 0 and 1. These are two different numbers that is allowed in binary because its base is 2. And only up to 1 we can add, that makes it total two different numbers. So if we want to represent this, we can say that 2 raised to the power 1 gives us the different numbers in it. So if we represent it as a power of 2, we will say that to represent binary number, we only require how many bit? 1 bit. Okay, because 2 raised to the power 1 is 2, and the maximum numbers of the maximum different numbers in binary system is only 2. Similarly, for octal, the base is like 8, and we said 2 raised to the power 3 is 8. So the maximum number of bits required to represent any octal number is 3. So in octal, we are having like from 0 to 7, and each numbers is represented in a bit of in 3 bits. Okay. Similarly, for hexadecimal, the base is 16. We are having different numbers ranging from 0 to 15, whereas A, B, C, D, E, and F, where A represent 10 and F represent 15. So to represent these 16 different numbers, we require how many bits? 2 raised to the power 4 is 16, and therefore required 4 bits. Okay. So in hexadecimal, we required 4 bits. In octal, we required 3 bits. And in binary, we required 2 bits. If that is clear to you, let us see the conversion and different technique. First of all, there could be 4 different types of conversion. We may convert decimal number to any number system, and vice versa, any other number system. Okay. And we can convert back any other number system to decimal. Both we can do. So let us take an example and understand this. For example, if suppose we want to convert 6, this is a decimal. We want to convert this into binary number system. Or let's suppose for any number system whose base is given as R. If base is given as R, what we do, we take that number 16 over here, we take that base over here, we go on dividing this, we write the like the quotient over here and the remainder over here. Suppose this is Q0, this is R0. Again, we go on dividing by R. This is Q1, this is R1. Again, we go on dividing by R. And this is Q2 and this is R2. We go on dividing unless Q2 become less than R. If Q2 become less than R, then if Q2 is less than R, then we go writing this way. And we say that this base 6 in 10 in any by number system whose base is given as R can be represented as Q2, R2, R1, R0. What I'm talking about, let us take an example and understand the thing. Suppose we want to convert, let's say, suppose we want to convert, say, suppose 17 in decimal system, we want to convert it to a binary system, into a binary number system. So we already know by what binary that the base is what? R is nothing but 2. So if base is given as 2, so what we have to do, we have to divide 17 by 2. And we will write quotient over here, remainder over here. To 2 8 is 16, remainder will be what? 1. Again, 2 4 is 8, remainder is what? 0. Again, 2 2s are 4, remainder is what? 0. Again, 2 1s are 2, remainder is what? 0. Now you see this 1 has become less than the base. So what would be our conversion? We will have to go from this side. So this would be like 1 0 0 0 1. So this is the binary equivalent of, or we can say, we can represent it like this. This base represent that this is a binary number representation is equivalent to 17 base 10. Let us now convert this 17 into hexadecimal. So by hexadecimal, we understand that the base is already what? 16. Now, before going to that technique that we have seen earlier, let us understand that in hexadecimal we can represent from number 0 to 15, and that to A represent 10, B 11, C 12, D 13, E 14, and F as 15. We are representing what 17. We want to represent what 17. For 17 again, what you have to do? Like you have to come back, like after 15, you have to come back to 0 again for 16 and 1 again for 17. You're getting my point, what I'm saying, what I want to say. For example, for 0 to 9, suppose we have 0 to 9. For 10, what you go? For what if you want to write 10 in decimal, what we do? Sorry, for 11 in decimal, what we do? This is 0 to 9 is already 10. Already 10 numbers. For 11, if you want to represent 11, what you do? 11 is written as what? 1 and 1. That is how we write 11. If we want to convert this into decimal, again, we will get the same thing. 10 ones are 10, remainder is 1. So this 1, 1 will represent 11 only. So if we represent 17 into base 16, we will get 16 over here. What we will write? 16 ones are 16, carry 1, 17. So this will what? 1, 1. So 17 in decimal will be equivalent to what? 1, 1, 11 in hexadecimal. So see, this is so this is basically the conversion, and similarly you can convert to any other means any other number system. That is, for you have to remember that this technique is used to convert what decimal number system from decimal to any other number system. Okay, so we have taken 17 and we have seen how 17 can be converted into binary and how 17 can be converted into hexadecimal. Okay, now let us take one more example wherein we are going to convert this, say 23.125 base 10 to binary. Okay, so how you will do that? You have to take the exponent and Mentesa differently. For example, the integral part and the decimal part separately. For integral part, what you have to do? 23 can be represented in the same way. 2, like 11s are 22, carry 1. 2 5s are 10, remainder 1. 2 2s are 4, remainder 1. And 2 1s are 2, remainder 0. So if you go this way, what you will get? You will get basically 1 0 1 1 1. So this is the representation for 23. What about 1.125? So to convert 0.125, what is the base? You multiply it by base. What you get? You get like 5 2s are 10, 2 to the 415, and 2 2 1s are 2, 0.250. So what was the decimal part? So the decimal part is just remember this part. What is this? This is 0. Now again you have 0.250 multiplied with 2. What you will get? 0.5. Again this part you remember 0. Again 0.5 multiplied by 2. What you get? 1.0. You have to multiply this term repeatedly by 2. Again, this term multiplied by 2. This term was multiplied by 2. So 0. When you multiply 0 by 2 is nothing but 0. So you have to stop over here. Why? How do you figure out that we have to stop over here? Either you get 1.0 with the decimal part at 0, or you repeat the same, like you repeat the same sequence. Like we have now 0, now 0, you 1. Again, you are going to repeat the same sequence 0, 0, 1. That means you have to stop over here. So for this part, for the integral part, we move from bottom to top, but for the decimal part, we will move from top to bottom. So the overall answer would be like 10111 dot 001 001. This would be the correct answer in base 2. I hope you understand this decimal part also. How do we convert it into any other number system? For example, if you want to convert to octal, the octal base is what? 8. So you have to multiply it by 8. You multiply it by 8, whatever is the integer part, you remember that it may be either 1, 0 or 1. So, or 2, 3, whatever, because in octal you may have different 0 to 7. So you may get 4, 5, 6, anything. Multiply, take this, multiply repeatedly until you get like this part as 0 or the sequence is repeated. Okay, this is how you convert any decimal to any other number. Let us take a few more examples. Suppose you want to convert 27 base 10 to any number system with base 4. So with base 4, again, what we will do, we will take base 4 over here, 27 over here. We have 6, 4 the 24, remainder will be 3. We have 4, 1 the 4, remainder will be 2. So the conversion in base 4 will be 1, 2, 3, base 4. So now let us see that how do we convert any other number system from any other number system to decimal number system. See, I'll give you a generalized formula and then you remember that. You might have done it so many times. For example, you want to convert 1, 1, 1. This is binary. How do you know that this is binary? Because like until and unless it is not given as base 2, it is difficult to say whether this is binary or this is any other number system. Why? Because this 1 is also present in the binary, in decimal, hexadecimal, octal, whatever base you have, for whatever number system you have, for base greater than 2, all this one is present in every number system. So if you write 2 over here, it means this is a binary. So if you have a binary over here, how do you convert it? This is equivalent to 7, but how do you get 7? What is the base? Multiply the base raised to the power 0 into first digit. Here base raised to the power 1 into second digit, that is also 1. Then base raised to the power 2 multiplied by third digit, that is also 1. So this is nothing but 1, this is nothing but 2, this is nothing but 4. And you add all this thing, you get 7. This is how you convert. So to convert any number, say suppose we have A3, A2, A1, A0, this A2, A3, A1, and A0 may be any number, A0, 1, 2, 3, 4, A, B, C, anything. And you have given the base, so to convert it, what you have to do, you have to take like a0 multiplied by base is r ki power 0 plus a1 multiplied by r power 1 plus a2 multiplied by r to power 3, sorry 2, plus a3 multiplied by r ki power 3, and so on. This is the conversion. Okay, for example, we have seen above 123. This was the base 4. If we want to convert it into decimal, what we will do? We have nothing but 3 into 4 raised to the power 0 plus 2 into 4 raised to the power 1 plus 1 into 4 raised to the power 2. This is nothing but 3, this is nothing but 8, and this is 16. So you add, you get what? 24 plus 3, 27. This is what we have converted 27 base 10 to any number system with base 4, that is 123. So okay, the number could be also of the form of like A3, A2, A1, A0 dot A hyphen 0, A hyphen 1, A hyphen 2, like this also. So for this, we have already seen that it may be like in the form of A naught R0 plus A1 R ki power 1 plus A2 R ki power 2 plus A3 R ki power 3 dot. What about this? So for this, we have like A hyphen 0 R ki power minus 1 plus A hyphen minus 1, so R ki power minus 2 plus A hyphen minus 2 R ki power minus 3. Accordingly, we will go on. So the above example, we have like converted 10111.001 base 2. This is the binary, and let us convert to decimal. So to convert it into decimal, let us first take this one. So we have 1 into 2 raised to the power 0 plus 1 into 2 raised to the power 1 plus 1 into 2 raised to the power 2 plus 0 into 2 raised to the power 3 plus 1 into 2 raised to the power 4. So this is nothing but 1, this is 2, this is 4, and this is 16. So this is what? 23. Okay, dot. Now let us talk about this. I've said that 0 should be multiplied by, what is the base? 2 raised to the power minus 1 plus 0 multiplied by 2 raised to the power minus 2 plus 1 multiplied by 2 raised to the power minus 3. Okay, so this term is 0, this term is 0, this is 1 upon 8. So 1 upon 8 is nothing but 23.1 upon 8 is how much? 8, 1. Keep 0, you have 0. 8 ones are 8. 2, 0 over here. 8 2s are 16. 4, 8 5s are 20. That is 0.125. So 23.125 in base 10 would be the conversion of this number. And we have seen this in the above example as well. See, we have converted 23.125 to this. So you have to remember these two things. First is what? We convert decimal to binary, or suppose decimal to any other number system. Any other number system. And the easiest way to understand this or remember this is like, just see that what is the equivalent of 4. Binary equivalent of 4 is nothing but 100, and you will come to know that the method that is used for this, the division method. Okay. Similarly, for any other number system to decimal, for example, 100 or 100 in base 2 is equivalent to 4. We use what? We use multiplication. Like r ki power a0 r ki power 0 plus a1 r ki power 1 technique. Okay. Now let us move to the another conversion. We have seen the two important conversion. Then we have binary to any other number system. And then we have any other number system. Any other number system to binary number system. Okay. See, when you have been given binary and you have to convert into any other number system, See, binary would be like this: 1 0 0 1 0 1 1. This is the binary because there could be only two possibilities of two different unique numbers, 1 and 0. So you have such streams. Okay. So you want to convert it. Let's say, suppose I want to convert it into base octal. So what is the base of the octal number? It is 8. How many bits do you require to represent an octal number? It is 3. Because 2 raised to the power 3 is 8. So we require how many bits? We require 3 bits. So you make grouping of 3 bits of this binary. This 3, this 3, this 3, and obviously this 3. There is no 3, add 0, 0. So this would be what? This would be 4, not 4. This would be 3. Convert this binary into number. This would be what? Again 3. This is 1. This is 1. So this number is equivalent to this in octal, basically. Suppose it was asked to convert into hexadecimal. In hexadecimal, how many bits do you require to represent any number in hexadecimal? You require 4 bits because the base is 16. To make a grouping of 4 bits now. Instead of 3, make a grouping of 4 bits. Take this 4 bits together. So this will now become equal to what? This is 2 raised to the power 0. This 1, 2, 4, 8. 8 and 3, 11. This will become 11. Again, you make group of 4 bit. So this will become 5. Now here you have 4 bit. To compute 4 bit, add 2 bit extra, you will get only 2. So 11 is not in hexadecimal is represented as what? B. Okay, A is represented as 10, B is 11. So 2, 5, B would be the hexadecimal representation. Now to convert this any other number system back to binary, you represent each number like in the bits. For example, I said I want to convert 2, 5, B into binary. You take each number B. B is what? 11. Represented in a 4 bits. 11 would be like 1 0 1 1. What is 5? Represented in the binary number with 4 bits. That is 0 1 0 1. This is 5. Represented in 4 bits 0 0 1 0. So the equivalent binary of this would be 1 0 0 1 0 1 1 0 1 1. Very easy to convert any binary into any number. In this, what you have to do, you have to understand how many bits are required and make groupings. You have to make groups. And to convert any number back to binary, just remember that number should be represented in how many bits. And then you represent that number in that many bits. For example, I say represent 1A into binary. So A is, I know how, what is A? A is, I mean 10. So represent A in 10. For 10, I will be having like, this is 4. Sorry. This is 8. This is 0. This is 2, 0. This is 1 0 1 0. This is 10. Okay. So for 1, I would only require 1 bit. But I have to represent this into 4 different bits. 0 0 0 1. So this would be the hexadecimal representation. Or instead of that, if we had like A and 1, so these 3 bits would be ignored because this is MSB bits would be ignored. So instead of that, if you have A1, so the 1 here now would be represented in 4 bits. And A would be represented as 1 0 1 0. So the overall binary conversion would be like 1 0 1 0 0 0 0 1. And that is the important point or important difference that you should know. So now let us talk about the complement. What do you mean by complement? We have often used this 0 0 1 1. If you want to make complement of this, we have 1 1 0 0. But have you ever like understand the technicalities behind this? How this comes? So for any number system of base R, okay, any number system for base R minus 1 is complement. R minus 1 is complement is given by R minus 1 is complement is given by what? Is given by the maximum number in that base R minus the given number. Minus the given number. For example, if we talk about the 1s complement, if we talk about the 1s complement of this number 0 1 0 1, and we said that this is a binary representation, base 2. So what is the maximum number in base 2 we have? We have 1. Only 2 different numbers are there, that is 0 and 1. So the maximum number is 1. We write 1 1 1 1 and we subtract the given number from that maximum number. Okay. So what we get? If you subtract, sorry, this is 1 1 1 1. So 0 1 0 1. So this is what we get, and this is known as the complement of this number. So for binary number, the complement is very easy. That we just complement zeros and 1. But like if this is the number and we have to find the complement, we do it the like 0 is replaced with 1 and 1 is replaced with 0, and what we have is the complement. But for example, for any other number system, for example, if I write that 5 4 3 2 1, this is an octal number base 8, and I want you to represent this in like the 8s complement, or sorry, the 7s complement. What do you mean by the 7s complement? The 7s complement means the 7s complement means you have to subtract the given number from the highest numbers in that base. For in base 8, we have numbers ranging from 0 to 7. The highest number is 7. We have to subtract this from the given number. So this would be like 6, 5, 4, 3, 2. So this is the 7s complement of this given octal number. Okay, now that is okay. So what if we want to find the 8s complement? 8s complement, which is nothing the base complement, RS complement, not R minus 1 complement, but RS complement. To find the RS complement, we first find the R minus 1s complement and we add 1 to it. So what you need to do, you have to find 7s complement to find 8s complement, that is this, add 1 to it. When you add 1 to it, it becomes 7, 5, 4, 3, 2. This is nothing but 8s complement. How do we find the 2s complement? Suppose we want to find 2s complement of this number 0, 0, 1, 1, 1, 0, 1. So the first thing is you have to find the 1s complement. The 1s complement will be what? You have to subtract the given digit by 1, or in binary just replace 0 with 1 and 1 with 0. So this is the 1s complement, add 1 to it. So what you will get 1, 1, 0, 0, 0, 1, 1. So this is 2s complement. So friends, I hope that you guys would now be able to find the complements of any number system. Suppose R complement you are asked, you can subtract that given number from the highest existing number, and R minus 1 is complement you can find. Similarly, first R minus 1 is complement need to be find, add 1 to get R is complement. Okay. Now let us see the negative number representation. That is also very important. There are basically three ways to represent the negative number. Three ways. Number one is called the signed magnitude. Signed representation, say. Signed representation. In this, for example, we have 3 bits. For example, we are having 3 bits. So the most significant bit, this is the most significant bit, MSB, and this is the LSB. The most significant bit is reserved to represent the sign. If it is 0, that means the number is positive. If it is 1, that means the number is negative. Okay. So out of the 3 bits, only 2 bits can be used to represent the numbers, and 2 bits can be used to represent how many numbers? Like in the 2 bits, you can represent 4 numbers. That is, you can have 0, 1, 2, 3, 4. So you can have 0, 0, 0, 0, 0, 1, 0, 1, 1, 0, 1, 0, 0, 1, 1. Similarly, you can have with the 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So this is nothing. In normal representation, this is 0, this is 1, this is 2, this is 3. This is 4, this is 5, this is 6, this is 7. But in signed representation, you see, this is 0 plus 0. We can say this is plus 1, this is plus 2, this is plus 3. But this is minus 0, this is minus 1, this is minus 2, and this is minus 2. So you see, in signed representation of a number, the positive numbers are written in the same way. Okay, there is no difference in that. 0 and plus 0 represented as same 0, 0, 0. 1 is represented 1 or a plus 1. Both are same, is represented as 0, 0, 1. But the negative representations differs. 1, 0, 0 in unsigned representation is 4, but in signed representation is minus 0. So for 3 bits, you are having, like, you represent it from plus 3 to minus 3. So we can say that for 3 bits, you can represent 2 raised to the power 2, say 4 minus 1 with a plus sign, 2 with a minus sign, 2 raised to the power 2 minus 1, that is from plus 3. This is nothing but 3, plus 3 to minus 3. So we can say that in signed representation of n bits, since 1 bits, we use it for representation of the sign. So we are left with n minus 1 bit. Like in 3 bit, we are left with 2 bits only. So with n bit, we can represent 2 raised to the power n minus 1, and 1 is used for 0. Like out of this 4 bit, 4 different representation, 1 we are using for 0. So therefore 2 raised to the power n minus 1, that too from plus 2, from plus this to minus 2 raised to the power n minus 1 minus 1. This is the total representation that can be done with an n bits, that is the signed representation. The another technique to represent the negative number is called as the 1s complement. 1s complement. Again, here also, the MSB will be used to indicate the number is positive or a negative, and the other term we will represent it as like 1s complement. For example, if we have like 1, 0, 0, 1, so this number is, the MSB is 1, so this number is negative. Now you find 1s complement of this, so this will be 0, 0, sorry, 0, 1, 1, and 0. So this represents nothing but 6. So this number represents nothing but minus 6. This is 1s complement. So in 1s complement, what we do, we represent the number is in 1s complement form. Okay. So here also the total number of the total representation that can be made is same like the sign representation. Okay. Here also we have two representation for plus, two different representation for plus 0 and a minus 0. Okay. But the other way of representing the signed numbers are 2s complement. So if we take this number only, let's suppose we take this number only 1001. In signed representation, it is going to represent as what? Minus 1. This is nothing but 1. And this sign indicate minus 1. In 2s complement, 1s complement form, we have seen that this is representing as minus 6. What about the 2s complement form? To represent 2s complement, we find it 1s complement first. So this is this, add 1 to it. So it is 1, 1, 1, 0. So this is nothing but equivalent to 7. So this number is representing what? Minus 7 in 2s complement. This is signed representation. This is 1s complement and this is 2s complement. So just remember in 2s complement, we have represent from negative 2 raised to the power n minus 1 to positive 2 raised to the power n minus 1 minus 1. Here we don't have the unique representation of like unique representation. We don't have the unique representation of plus 0 and minus 0. That we have two different representation for 0. We do not have that here. We have only one representation for 0. Therefore, we have the range from 2 raised to the power n minus 1. Not minus 1 over here is not present. To plus sign 2 raised to the power n minus 1 minus 1. So now you might be a little bit confused when I say that there is no unique representation of 0 in 2s complement. So let me make it clear for you. See, first of all, for positive number, either you are representing it in a signed representation or 1s complement or 2s complement, there is no difference in it. For example, 0, 0, 0, 1, this is plus 1, irrespective of which format you are representing it. Either you are using it as signed representation, 1s complement or 2s complement. Only the thing you have to worry is about the negative part. So when I say 0, let us talk about 0. When I say 0 and I say it like this, 0, 0, 0, 0 and 1, 0, 0, 0. So we say that this is nothing but plus 0. Okay. And this is nothing but minus 0. If we talk about the sign representation. So in sign representation, we have seen that there are two representation of 0. Therefore, we have like 2 raised to the power n minus 1 from plus minus 1. This is dedicated for the representation of 0 minus 1. Similarly, for the minus sign also, we represent minus 1. Because we have already seen here that with 2 bit, although you can represent 4 different numbers, but you have to subtract 1 because you can represent only 1, 2, 3 and 0, like from 0 to 3. From 0 to 3. So for 0 representation in positive and 0 representation in negative, we subtract 1 from the positive side and negative side. So it ranges from 2 raised to the power n minus 1 to minus 1 to 2 with negative sign 2 raised to the power n minus 1 minus 1. Now for 1s complement, say this is and this is. If we talk about the 1s complement, this represent as plus 0. Now this is a negative number in 1s complement. How do we know that? By the MSB, which is 1. So now this would be the number that will be the actual number. So represent this in 1s complement. Let's take 1s complement. What is this? This is 0. So this is nothing but minus 0. Now in 1s complement also we have a two representation of 0, that is 1 for plus 0, 1 for minus 0. So I said that 1s complement also the number range will same as the sign representation. But for the case of 2s complement, if this is 0 and this is 1, 1, 1, you say this represent as what? Plus 0 and this represent as what? Take as 1s complement and add 1 for 2s complement. This is nothing but 0, 0, 1. So this is nothing but minus 1. This is a negative number as indicated by 1 in the MSP bit. And this represent basically 2s complement of this is 1. So the number is minus 1. Now you see, we have only one representation for 0. That is in the plus side, plus 1. And there is no minus 0. Instead, we have a minus 1. So when we say that in the minus side, we have the number ranging from minus of 2 raised to the power n minus 1. There is no minus 1 over here. Okay. 2 plus side, we are having plus 0 representation. So 2 raised to the power n minus 1 minus 1. I hope now this is clear to you. Now let us do one question so that the things become more crystal clear. Suppose we have root over 41 and that to base b is nothing but 5 base 10. So we are interested in finding the value of b. So let us represent this in decimal, and we have known that to represent any number in decimal, what we have to do is multiply a0 r0 plus a1 r1, where r is the base and a are the digits. So since this is the square root of the 41, so to remove the square root, let us take the square of both sides. So what we have is 41b is nothing but 25 base 10. The square of 5 is nothing but 25. Now converting this into a decimal, what we have as 1 into base raised to the power 0 plus 4 into base raised to the power 1. This is nothing but 25. Now this is base 10 and this is base 10. So we have what? 1 plus 4b is equal to what? 25. 4b is equal to what? 24. And from here we get b value is equal to 6. So this such a types of question like conversion from one to another, or the negative numbers representation, it may be in the question given at this is 1100 is represented as 2s complement. So what is it actual representation in decimal? So you need to understand that this is the negative number, and 2s representation, it will be actual number would be represented as 0011, and add 1 for representing it in 2s, so we get 0. This is 110 So this number is nothing but -4. So this type of question you might expect in the exam. So guys, this is all with the number system, and with this we are going to end this digital electronics. I hope you enjoy the lectures. Thank you.